Welcome, everybody. Thanks for coming out on the RRR week. So I tried to put together a couple of topics that were on the list that people sent, and ended up with too many slides, so we'll see what happens, but we'll go with it. So what I decided to talk about, I was going to talk a bit about peer-to-peer systems, going to talk about many core operating systems. We'll hopefully try to get to real-time and trusted computing, but I actually have 88 slides, so we'll see what happens. Fortunately, you're not actually responsible for this on the exam. So what does peer-to-peer actually mean? So peer-to-peer usually means something about fully equivalent components. So you have a set of services, a set of clients on a network, and every one of them is identical in some way, but they're communicating together to perform some action, okay? And so many interacting components, the system's a set of equivalent nodes. You could say this is the all nodes are created equal. Any structure that might be in the system as a result has to be self-organizing in some way. So if it turns out that it's useful for some nodes to be more important than other ones, typically that is something that comes up from the bottom as part of a negotiation process amongst nodes. Okay, you could imagine there might be a leader election or something like that that goes on. So I don't know if I've mentioned this before, but this was my favorite Dilbert cartoon of ever, where basically they sit around and say that their project is a paradigm, which basically means a pattern, and nobody really knows what the word meant, which is pretty funny. But the old view of peer-to-peer systems was kind of originally a bunch of, flaky high school kids stealing music, right? And this is probably the view that you've often heard with Napster and Kazaa and several of these, BitTorrent. Somewhere around the turn of the century, basically there was a new view that kind of developed in the research community, which I thought was quite useful. And one of the views of peer-to-peer systems was it was really a philosophy of designing systems at extreme scale, where extreme scale now means somehow there's 1,000 or 10,000 interacting components that are all doing something useful. Another aspect of peer-to-peer systems is also this notion of a probabilistic system design when it's appropriate. So we might talk about getting a result because it happens with high probability, not because it happens for sure. Okay, and when you've got 1,000 nodes or 1,000,000 nodes, maybe that with high probability is extremely high probability. Also, what came out of peer-to-peer was a lot of new techniques for dealing with unreliable components. So there was a refocusing of let's build things in which the components are fundamentally unreliable, but the end product is reliable. And that's kind of a different viewpoint from what you're often used to today is, well, this computer just doesn't crash, I say that in quotes, and therefore I can rely on it, right? So the notion that the system components are reliable up front is kind of the one that's often taken, except for certain communities where they really care about reliability. Whereas in the peer-to-peer realm, the assumption was from the beginning the components are flaky, and we're going to build a reliable thing out of them. Okay? And I would say it was a rethinking of distributed algorithms. So I talked about Byzantine agreement earlier in the term. Byzantine agreement had been around for quite a while, but the peer-to-peer community sort of brought it up again and said, gee, let's see if we can use Byzantine agreement in this global scale to do something useful. And then other things that were kind of interesting is people start applying sort of ideas of biology and physics and game theory to big systems, which got kind of interesting. So for instance, I often like to talk about the entropy of a system storing data. And data decays over time, and the trick of the system is to keep suppressing the entropy so you don't lose your data. So there's a lot of these kind of analogies that came into play. By the way, feel free to ask questions. So why was there hype around peer-to-peer? Well, Napster was this file sharing system. And basically, it got sued by the music companies, and there was a really big deal about that. So I don't know if any of you were looking for music in the early 2000s or late 90s, but Napster was the place to look. All right, and it also kind of provided a way for a bunch of people to easily contribute to a global system that was sort of, you could almost look at it as cyberspace, right? The cyberspace of music. And it served a very high demand niche, which was kind of this online jukebox idea. Another angle that was very interesting about peer-to-peer systems was this whole anonymity, privacy, anarchy. Okay, so the nice thing about peer-to-peer systems is somehow you could put together a system where people could share information and not give up their identities. And maybe this is some sort of libertarian dream of freedom from the man or something. I actually believe it also kind of had an interesting flair about how to deal with countries that have censorship and can you get your information out. Okay, and so there's Freenet was one particular system that was really targeted at that, as was Publius. And of course, the more that you build anonymity into the system, the more, and then people sort of take copyrighted information and put it into an anonymous system, now you got kind of a mess, right? Because potentially you've got actual copyright violations, which isn't what the system should be used for, being used in a way that it's very hard to track down, and suddenly you get, the RIAA basically is suing people and shutting down Kazaa, and that goes on to this day. So it's got its positive side, it's got its negative side. And also about this time, computing. So SETI at Home was anybody here installed SETI at Home on their systems ever? Okay, not too many of you, but SETI at Home was kind of this cool idea that you're going to provide your computing cycles when they're free to searching background radio telescope readings to see whether you see signs of intelligent life. And it was kind of fun because it had a cool display that would come up as a screensaver and kind of show you the data it was crunching through. And then, businesses around the 2000s, just before the big crash of the dot-coms, had started discovering computing at the extreme scale as well. And so peer-to-peer looked like a way to maybe help provide some of their business logic. So I would say all of these things right around the turn of the century kind of all fell together, and suddenly peer-to-peer was either interesting or somebody to sue or something, okay? And researchers really jumped on it. Okay? Questions? Okay? So let's focus, first of all, what I want to do is I want to focus on a particularly simple system, which is very powerful, called Chord. And then I'll tell you a bit about OceanStore, which is a research project I had, and we'll go with there. So the basic lookup problem that we're trying to solve here is a very simple one. We've got the cloud, and unlike Microsoft reinventing the word cloud, I don't know if you've seen any of those commercials, but it's not clear what they mean by the cloud. It seems like it means the internet or something. But here, I actually mean a bunch of storage servers that are out there in cyberspace, and they're contributing in some way to this global system. So I could say this really is the cloud. And the idea is that some publisher is publishing something like saying, well, the key is the name of some song, and its value is its data, and it sort of puts it into cyberspace. And somebody else says, look it up, give it back. Okay? So this lookup problem, you could imagine being solved in many ways, including the simple way where there's a database out there and everybody contacts one node, right? So we're going to assume that that's not an interesting scenario. Okay? Is everybody with me on the problem here? If you read a lot of science fiction, I mean, this is kind of a view of the black box of what cyberspace is. You put the stuff out there and it comes back. So Napster was sort of halfway between the client server in the traditional sense and peer-to-peer, which I'm going to talk about in a moment, in that there was a centralized server, but the only thing this server did was location services. And so if you had a publisher here on node 4 that had some data, all that they did is they told the centralized name service what data they had. They didn't actually give the data to the centralized name service. And a client who's trying to look up the data would contact that name service and do a database search and then send a query to the publisher of that data directly to get it back. Okay, so what we've got here is kind of we're coordinating a system of all of these nodes that are actually storing the data, and a centralized database name server is helping set up pairwise transactions, if you will, between the client who wants a song and somebody who's got a song. Okay? Now, this is simple. That's probably why it was the first one that got a lot of notoriety. But it's got order n state, so this database has got to keep track of everybody. And it's got a single point of failure, which is exactly how it got shut down eventually. It was very easy to go after Napster because there was one database. Okay? Now, other options, so Gnutella was an alternative that was out about this time, and the notion here was a flooding. So if you have some publisher at N4, the way client N5 would actually find the data is they'd flood queries to everybody and say, hi, do you have what I'm looking for? Okay? So this is extremely simple. It's also extremely fault tolerant because typically these links that are used for the broadcast tree are built on the fly and over again. And so, so it's very reliable, but, in worst case, you're sending a message to every node in the system. So this is not very desirable. So, routed queries, or sometimes often called structured peer-to-peer, is something different, which is basically a publisher puts the data into the network and publishes so it actually routes to some node in the network rather than being stored necessarily on the local node. And the client executes some algorithm that routes the query to that node. And as a result, because of the structure of the underlying algorithm, the query and the data meet up somewhere in the middle of the network, and you get your query satisfied. Okay? Questions? Is everybody with me on this distinction? So basically, peer-to-peer systems often have this property where the underlying structure of the routing algorithm is actually the thing that matches a data in a query up. Okay, and what I want to do is I want to tell you about Chord. How many of you know about Chord? Very few of you. Good. So Chord is what I would say kind of the canonical example of something that works like this, and it's extremely simple, which is why I like to talk about it. And so I actually grabbed some slides from the original Chord talk back in 2001. And so let's talk a little bit of how this works. So again, we're going to do this matching, right? We're going to store data in the network, and we're going to find data. And how do we do that? Well, a key in this system is going to be a SHA-1 hash over the kind of key that a human might care about. Okay, remember SHA-1 is one of those secure hashes we talked about. So for instance, a node identifier is going to be a SHA-1 hash of its IP address. Okay, and both the key, which might be the data you're looking up, and the node identifiers are uniformly distributed kind of in 160-bit space. And the reason they're uniformly distributed is because of one of the secure properties of a hash that I told you about, a secure hash, is it tends to spread the bits randomly. So if you change, a tiny bit, like a single bit in this IP address, you tend to change over half of the bits or about half of the bits in the hash. Okay, so by hashing the name of the file and the name of the nodes, you end up with kind of uniform distributed keys in 0 to 2 to the 1/60th space. Okay, is everybody with me so far? Now, both of these are thought to be in the same ID space. Okay, and the question is really how do we map key IDs, which is the data, to node IDs, which is the potential people who can store it. So let's go back to this previous picture here for a moment. Notice that the key, which is human readable, is known by both the publisher and the client. Once we SHA-1 hash it, the real question is, which of these nodes is going to store the data based on the SHA-1 hash of its title? And there's going to be some algorithm that lets us find that particular node. Okay, and the way to do this in Chord is extremely simple. So we basically build a ring. Okay, and the ring is kind of, now I have 7-bit space here because that was kind of what they talked about in the talk, but this could be 160-bit space, for instance. And basically all of the keys in the world are in this ring. So we basically have 0, 1, 2, 3, 4, 5, 6, 7, all the way up to 2 to the 1/60th, for instance. Here, let me actually change this while we're talking here because we want to make sure that this doesn't confuse you here. Sorry, I was using somebody else's slides here. So, okay, Now, what does this mean? This means that every key has a place on this circle, including all of the nodes. So here's node 32, node 105, node whatever. They all have a spot on this, which is the hash of their IP address. And the data, which is the keys we're looking for, also have spots on this ring. And we can talk about an ordering. Okay, so in particular, which node stores this data is the node that is the immediate successor of the key. Okay, so notice in this particular example here, I have 3 nodes. And those 3 nodes, there's only 3 nodes in the system. And therefore, key 5 and 20 end up on node 32. Key 80 ends up on node 90, etc. Okay? Questions? Now, the trick is, how do you do this in a distributed fashion? Okay, so obviously in any real system, there's thousands of nodes, tens of thousands or millions of keys, and somehow we've got to automatically set it up so that this just works. Okay, and that's what Chord is about. And the basic lookup idea starts with all of the nodes in the system. Now I've added a few more here. All keep track of exactly one thing. They keep track of their successor in the ring. Okay, so imagine, and I'll tell you how to do this in a moment, that node 120 knows that the next node in the ring is node 10. And node 10 knows that the next node in the ring is node 32. Okay? So how do we do a query? Well, so node 10 says, where is key 80? Okay, now notice that, for instance, node 90 has key 80 on it, okay, because there is no node 80. So what we really need to do is we need to route to node 90. So what happens? Well, here's the simplistic algorithm. Node 10 says, well, 80 is bigger than me, so I'll route to my successor. I'll route to my successor. I'll route to my successor. Oh, I got it. Node 90 has key 80. Okay? Now, very simple algorithm, but what's a little unfortunate about this? Anybody? Yeah. So if we lose a node, we're in trouble. What else is unfortunate about this? Yes?
You have O of n, worst case, like lookup.
Yeah, so worst case, so both, if we lose a node, we're toast, and we have order kind of n hops to find the data. Okay, so this, especially if you've got thousands of nodes, this seems like a very bad algorithm. Any other things that are bad about this? Those are kind of the 2 big ones. But okay, so how can we fix this algorithm to be faster? Now, first of all, before you answer that question, I want you to notice that if we can somehow guarantee that we have a successor link, then I can always find every key in the system, right? So it seems like from a correctness standpoint, making sure that these links are good is important. So correctness, the links are important around the ring. But what about performance? How could we make this faster? Go ahead. So one thing we could do is every node could keep track of every other node. Okay, so for instance, node 10 could have a pointer to every node, node 32, 60, 90, 105, 120. It could look through its list and basically decide that node 90 is the one that is going to have key 80 by just looking that it's, key 80 is bigger than node 60, less than node 90. It must be node 90. So that's unfortunate in why? Why would that'll work, but why might that not be a desirable technique? Yes. Right. So in other words, the state is actually order n squared because every node is keeping track of n other nodes, right? Now, that being said, by the way, I will tell you that some of the later peer-to-peer systems had a topology that was effectively that, where it evolved to where everybody knew about everybody else. But what would be a less expensive thing we could do? That might not, so that, by the way, would be order 1 hop, right, to get somewhere. What could be order, say, log n hops? Anybody? Go for it. Okay, how could we make it like a tree? Okay, but let's stick with the circular topology here that we've got, just the ring. Yeah. Okay, suppose we know the person across from us. Then what? Which half is it in? Exactly. So by the way, this is kind of the simple algorithm. You sort of say, well, I know who my successor is, and if my ID and the successor fits in this range, then I know that the key is on n, and so I'm good to go. Otherwise, I have to call and look up. Okay. So yeah, we know who's across from us. All right. So for instance, node 80 might know the guy who's directly across, and then the guy who's in the quadrant, the quarter, and the 8th, and the 16th, and so on. Question? Yes.
So doesn't this kind of mean that you need the entire space to be populated?
Well, that's a good question. Does this mean you have to have the entire space to be populated? No. So for instance, suppose that there's a node here at 120, but there isn't one exactly at half. What you want is these are called fingers, by the way. You want a finger to a real node that's as close to a half as possible. Okay, so the concept here is go halfway, then quarter way, and so on. Okay, but that has to be adjusted for the fact that the real nodes, there isn't a node in every spot. Okay, is everybody with me on this? So now we kind of work our way to something that's log n kind of. Okay, and the way to think of this, by the way, is the way I like to think of this is if I'm starting at node 80 and I'm going to some other node, what I'm doing is I'm actually bit correcting. So the first hop, I go across the ring, which means that if I have a 0 and the guy I want has a 1, I'm correcting the first bit. And the second hop corrects the second bit and the third bit and so on. And so eventually I've corrected all the bits and I find the guy I'm looking for. Okay? Now, so here basically you can say, the way this lookup works is I look in my local finger table, I find the highest node such that it fits kind of the right range here, and if n exists, I call lookup ID on n, so I send the query to n, and he deals with it. Otherwise, I assume that the node is on my successor, and I return the successor. Okay? And notice that this return my successor says, even in the worst case where there isn't a good finger, I still work my way around the ring. Okay. Now, so effectively what happens is you end up with something that takes order log n hops to get to where you want, rather than, for instance, in this scenario where I'm looking for key 19 and I start at node 32, I actually have to work my way all the way around with the linear algorithm, but with this logarithmic one, I'm much faster. Okay. Now, the Chord paper basically gave an algorithm for finding these nodes. Okay, and you can imagine, let me just give you a notion of how this works. Suppose that node 32, how did it originally find out about node 99? Can anybody give me an algorithm where it might have found out about a node that's all the way across the ring? Yes?
Like if it had requested something and then node 99 talked back to it.
Yeah. So take node 32. How do I know what directly across the ring is? I essentially flip the top bit. That's directly across the ring. Now, there may or may not be a node there. What I do instead is I do a query for the key that's exactly across the ring, and I'll end up with the node that's closest to it. Okay, so the same mechanism I can use for queries is what I use to find the finger table. Okay, and it's self-adapting in that sense. All right, now, let's look at how a new node enters the system. So the way a new node enters the system is, for instance, I have node 36. I have these pre-established nodes. What happens is node 36 finds any node that exists and makes a query and says, I want to find myself. And eventually what happens is node 36 says, find myself, and it gets back node 40 should have you, if you were a key stored in the system, in which case now it knows to make a pointer to node 40, and now there's enough state to basically fix up the pointers, and we've just effectively inserted a new node again by doing a query, but this time doing a query on my own name. Okay? Questions? Does that make sense to everybody? So basically, by transforming maintenance of the system into queries about certain pieces of information, I basically can build up all this state automatically. Now, of course, we might actually have failures if we're not careful. So for instance, if we have pointers to nodes that are dead, we could end up routing to the wrong place. And so we have to be a little bit careful never to overroute. So we all, worst case, we take the shorter hop. Okay? And we would like to have a system that self-corrected. So as soon as, say, node 85 and node 102 went down, the system kind of would close up behind them and fix all of the links. Right? And that's really about what the Chord algorithms did. And there's some very interesting dynamic algorithms that on the fly continuously correct as nodes fail. Okay? Now, somebody tell me there's a different problem here which we haven't solved. Suppose node 85 is storing a bunch of data and it dies. Then what? What happens? We lose the data. So what I've described to you here is not quite a good system, right? It's non-redundant. And remember how we were assuming that basic components of the system are likely to fail? This doesn't sound like this works. Okay? And so one way to do this is instead of knowing only your immediate successor, you know n successors. Okay? And if you know n successors, then you're able to close up the route around missing nodes, because if a node dies, you can route right beyond it. Okay, so you have enough information to keep going, and you make sure that every one of the successors has all the information that the root node or the original one you were routing to does. So if you have 3 successors, that means that rather than there being only one node with the data, now there are 3 nodes. And effectively, I've got extra redundancy there. And when a node fails, I can take one of those redundant copies and restore it so that I have 3 nodes for every node. And I can make repair my copies so that I always have 3 copies of everything, or n copies of everything. Okay? And in fact, in many systems, we actually talk about the leaf set instead of successors. And what the leaf set is it's just, say, if you imagine the root node is the one that would store the data, the root node keeps track of some number of nodes on either side in the ring. Okay, and it's the leaf set that holds the data. Okay? And when a node fails, everybody in the leaf set can handle queries for the dead node because they all have the same data. So if the fact that you can't get to the original root node, but you can get to one of the leaf set, you got your data. Or the leaf set can be queried to retrieve the missing data when I'm repairing a failed node, or the leaf set can be used to construct a new leaf set. So all 3 of these properties are good. Okay? So in fact, if you look, here's with the leaf set, basically you're mapping hash values to spots on the ring. And the leaf set is successors and predecessors of a given root node. And so you could say it looks like this. If I start a query, I have the green nodes are my leaf set. So in addition to myself, I know about 2 people successor and 2 behind me. And that will, at that point, but I also have fingers, so I can go forward to one of the fingers that's useful. That node has its own leaf set, and again, I've got fingers. And at some point, I get to a point where it's the leaf set that knows where the data is, and I don't use a finger, but rather the leaf set. And so I won't go into this in any further detail, but you can imagine that an algorithm like this is very resilient to failure. And so I can actually cut out nodes, and the system will close up behind them and repair the data and keep working. All right, and this is Chord. And everybody see where the name comes from, obviously, because the fingers are chords of the ring. Questions? That's all I'm going to say about Chord before I pile into something else. Questions? So there's a good paper. If you were to search for Chord and put in mit.edu, all of the original papers are there. There's quite an interesting website. You can download Chord if you want to play with it. There are versions of it that are there. And they've been run with thousands and tens of thousands of nodes up, and it just works, which is kind of cool. And it's self-repairing. Okay. So, dump. Administrivia. Final. Week from Thursday. Okay, I only have one person told me that they had a conflict, which I remember from the beginning of class because they have another class that's on top of ours. I sent them mail today, so if you are them, make sure you see that email. I don't know what to say other than this. You need a dumb calculator, 2 sheets of notes, both sides. All material from the course except for today is covered. Any questions about this? 10 Evans Hall? No? Okay. Don't forget your calculator. You'll need it. Code is due tomorrow for Project 4. Final report is due on the 8th. And make sure you fill out all your group evals. So do not leave the term or cross the final without filling out group evals for everything, okay? That will be bad. And it's very hard to get evals from people after they've left. So are there any questions on that? I think our group eval system's still working, right? Okay. Anybody had any trouble with group evals recently? No? Okay. I will have office hours. Somebody actually came in today at office hours. I'll have office hours still on Wednesday. Or if you really can't make office hours and you have a question, just send me email. I'll be around. So, you know, and I'm sure the TAs also would be around if you have any questions. So feel free. Come by and talk about whatever. If you want to look over old exams or ask me about the meaning of life or whatever. I may give you an answer if you ask me about the meaning of life, and whether you like it or not, who knows. But all right. And then last, please get any regrade requests in by Friday. I guess maybe I found out that we don't actually have Project 3 back yet, according to people, but it's done. So I have to find out why it's not in the system. Did we get the notes back to people? So everybody got their Project 3 notes. The grades are just not in the system. Is that correct? Okay. We will correct that very shortly. So try to get regrade requests for everything up to Project 4 in by Friday, and we'll let you do regrade requests on Project 4 up until the final, which is only a week from Thursday. Okay, the term has gone very quickly. All right, so if there aren't any administrivia questions, then I'm going to go on. So round about the .com craze, I had a project called OceanStore, which was smack in the middle of the peer-to-peer research domain, and we used some of the ideas from Chord, and we actually had something called Tapestry, which was a little more complicated. And we sort of tackled this notion of cyberspace a little further. You know, how does data get preserved for the very long term, where 1,000 years was the target? And that was called OceanStore. And we kind of had this notion of almost a utility-based infrastructure where this is a very old slide now because Pacific Bell doesn't even exist anymore. But the notion was that there'd be these overlapping service providers, and you would be paying one of them for your service, even though your data was stored quite widely to make it stable. And as a result, you would be talking to Pac Bell, your data, here's a piece of data on a portable device. It would be automatically replicated, and Pac Bell would be making micropayments to other utility providers to make sure your data was stable, and other people could now share it no matter where they were in the world. Okay, so this is the basic utility idea. And kind of a storage federation was what we were targeting. The administrative domain here is the different storage providers. And so basically there's no administrative boundaries here that can't be crossed. And finally, we had a contractual quality of service view, which is you put your data into the cyberspace or into OceanStore, and the service provider that you're paying, say Pacific Bell, is the person who's making guarantees about whether your data will be around when you go to look for it. Okay, so, and I like to think of that as they're the person you sue if your data goes away. Okay, and what we wanted to make sure is we had strong enough technical mechanisms that you could actually implement something like that, where a company could provide contractual obligations that the data wouldn't be lost. Okay? Questions? All right, so this is how I always viewed cyberspace when I read about it. Okay, it's like the data is just out there, and it won't get destroyed no matter what happens. Okay, and I don't know. You could say, well, we sort of have that now, but there isn't really a guarantee that your data will be there when you go look for it, right? If you store in Google, or you store on Yahoo, or you store on one of the picture sites, they don't actually guarantee they'll never lose your pictures. Okay? They sort of imply that it's unlikely, but they don't actually make any guarantees about it. And in many cases, your pictures are stored at exactly one site, so there could be, they could be lost. So the idea behind OceanStore was everyone's data one big utility. And so then we could say, well, if it's everybody's data, how many files are actually in the OceanStore? Okay. Well, assume that there's about 10 to the 10 people in the world, so we were rounding up a little bit. Say you have 10,000 files per person. How many people have 10,000 files? Probably many of you, right? Easily. Suppose you multiply these together, you get about 10 to the 14th files in the OceanStore. Okay? And now, this might be a stretch. Suppose you say we have a gigabyte for each one of these files. Okay? So that's a little bit of a stretch, although if you're starting to keep videos, maybe not so bad. So when you multiply all this together, you end up with a mole of bytes. Okay? And that was kind of, and if you remember a mole, 6 times 10 to the 23rd was basically, a liter of gas was how many molecules were in there, right? You remember that from chemistry. And so a mole of bytes was really our target. And when you think of a mole in the, as a liter of gas or whatever, it doesn't seem that many, right? It doesn't seem that big. And a yottabyte, which is actually 10 to the 24th, is something people do talk about, okay? Although we haven't quite gotten there, but it's not inconceivable. And so, truly impressive number of bytes, but it's small relative to physical elements. So if we ever got down to where we were storing things at the size of a molecule, maybe that's not so crazy. Okay, so we thought we would think big. Okay, and so now if you have a system that's got this much in it, how do you possibly store all that data? Okay, well, one of the things is if you put the data into the OceanStore, you really want automatic maintenance. Okay, and so if you have billions of servers spread around the globe and they're all handling everybody's data, and a server fails, you do not want to wait for your service, IP guy to go and repair the data. Okay, they can't be anything done by hand. Okay, there's just too much data. And so basically that led to a philosophy that basically the system needs to automatically adapt to failure, needs to exclude malicious elements automatically. So if there happens to be servers up that are bogus or trying to break into the system, that they should just be excluded. It should repair itself automatically, and it should incorporate new elements. So hey, I'm Pac Bell storage provider. I just brought another 1,000 servers online, and they just work. I don't have to go to much work to make this all sort of tie together. That was kind of our view. And also, obviously, the system ought to be secure and private. So if I'm going to trust my data by putting it out into the world, it better be the case that it can't be broken into easily. Okay? And basically, this was my sort of other technique, was I'm in view of the pyramids. My thought was, gee, you ought to be able to have your data last for 1,000 years. Okay, so this maybe is a ridiculous number to talk about for data storage, but what kind of data storage guarantees do you have today? Does anybody know how long does a disk drive last? What's the stated spec? How much? Who said 10? Okay, no. No, better than a year and a half. So spec's about 5. Okay, so when you put data on a hard disk and you think it's safe, you ought to rethink that. Okay? Because disk drives are actually only spec'd to last for 5 years. And it used to be that people put storage on tape. Okay, and tapes are even worse because what happens is if you could even possibly get the data off the tape, because the tape is good, you run into the problem of I can't find a reader that still exists anymore because the tape readers don't, they're gone. So, so somehow this has got to just work. And that was sort of our view. And so here's an example where we have a bunch of clients and the OceanStore. And the notion here was that security, access control and so on, was really gotten through data encryption. So if you encrypt your data and put it out into the OceanStore, then the data is secure, assuming that your encryption algorithm isn't broken. And potentially, have cryptographic hardware, which we might have time to talk about at the end of the lecture, I don't know, that would allow you to make sure that if I want to share my data with somebody over here, I give the keys to a secure part of the hardware, not to the OS, and the hardware can decrypt for the data that I actually want to talk about without giving that key to the operating system. Okay? But encryption was the mechanism here for protection. And then OceanStore, with its adaptation and self-repair and all that sort of stuff, could work in the background making copies of encrypted data, spreading them around, making sure there's enough copies, caching data close to your system so that it is high performance, and so on. But that's all an optimization, whereas the correctness aspect, which is the privacy and the security of the data, is handled by the way we put the data into the system in the first place with encryption. Okay? Is everybody with me on that? So OceanStore became an optimization problem of how to take a bunch of servers and turn them into a system that could find the data when you wanted it, that protected it by making lots of copies of it. Okay? Now, what were some assumptions? So one of the assumptions we had was the notion of an untrusted infrastructure, and that was that the OceanStore is comprised of untrusted components, individual hardware has finite lifetime, and all data is encrypted. Okay, and so you can kind of see that if the infrastructure is untrusted, we need to have these pieces. Okay, we have to assume that the data is encrypted, because if you can't trust the server, it's easy for it to get broken into, and then your data's gone. Or I mean, it's not private anymore, at least, right? Or if I can't trust the hardware to not crash, and I put some crucial piece of data on it, and then it crashes, and my system doesn't expect that, then I could lose data. Okay? So I have to be careful. The second thing was this notion of mostly well-connected, which was a little bit of a stretch back in 2000, much less so now, which is that basically most of the time there's connectivity available to you. Like this, you know, my Sprint phone has 3 or 4 different types of connectivity that it can make, and it can switch between them. Okay? And pretty much the only places that I don't have connectivity is some flights which don't have Wi-Fi. You know, they're starting to even talk about putting Wi-Fi on flights. So this notion of mostly well-connected basically allows us to start running algorithms that are making sure that my data gets replicated so it's not lost. It sort of pushes it out to the infrastructure as soon as possible. Okay? And then we had this notion of promiscuous caching, and what this really meant was there are servers everywhere, and we were talking about servers potentially in the wall and in the room and whatever. And what we would do is we'd cache your data close to you as a way of making sure that you had high performance. So even though the data was out there in cyberspace, we'd always have local copies to make sure that it was fast to access. Okay? And the equivalent, by the way, today, which is going to happen very soon, I think, is, of course, flash on phones keeps increasing, or flash on little handheld devices. So very soon you might have, you know, a terabyte of flash on your phone, and the trick is the permanent copies are in cyberspace, and the flash that's on your phone is purely a cached copy of the things you're likely to want quickly. And if those algorithms work right, then every time you go to look for data, even though it's out in the cyberspace, it's very quick to access because it's purely in your cache. Okay? So the final thing was, we found that you could not actually build a complete system out of these assumptions. Okay? If you really had a truly untrusted infrastructure where nothing is trusted, it turns out you could never make the system really bring your data, really guarantee anything about your data. And so that was where the responsible party came into play. And this was that there's some organization that you're paying, and they're giving you a contract that says, we will make sure your data still exists. Okay? And that responsible party is the one that I'm going to show you in a moment, is responsible for running the Byzantine agreement algorithms to make sure your data is updated properly. Okay? So these are kind of the peer-to-peer assumptions. This one is more of a quality of service assumption. And so we were different than a lot of other peer-to-peer folks in that they would say, well, with pure peer-to-peer, we can make everything guaranteed probabilistically. We wanted to throw in the quality of service one to really have somebody who was responsible for making sure everything worked. Okay. So how did we find data? Well, I showed you Chord. So Chord is your mental model of key lookup, hopefully. Now, we had a little bit of a twist, which we call decentralized object location and routing, and we had something which was, I guess, a research competitor to Chord called Tapestry that had a slightly enhanced property, which was, imagine that we have, these are copies of some data item that's, the red ones are copies, the green ones are copies, and the purple ones are copies. So this is only 3 different unique pieces of data, but lots of copies in the system. And what Dolar, decentralized object and location and routing, did was it allowed you to put a query into the cloud that would get routed to a local copy. So I would say, here's a hash over my data that I'm interested in, route it through the cloud, and the GUID one happens to be the red thing, and what it would do is it would find the closest red copy. If somebody else made the same query somewhere else in the world, they get a different copy. And since these are identical copies, that's fine. And so as a result, we would actually get locality out of this system. Okay, but it's exactly like Chord, which we told you earlier, where you put the data into Chord by routing it. It sort of gets stored at the roots in the leaf set, and then when you make a query, you route to the root in the leaf set and get your data back. Same idea here, but the actual locality component, which I'm not going to go into in detail right now. And then, of course, you could look for different things. You could multicast to multiple copies, etc. Okay, questions? So think of this like an enhanced version of Chord with locality properties. Okay? And we actually could get some pretty good stability even when nodes are failing. So here's a situation where we're doing a bunch of lookups, and 20% of the nodes fail, and then 50% new ones join, and then a bunch of ones are failing continuously. And essentially, we would get close to 100% lookups all the time. And if you failed on a lookup to find some data, you just had to retry it, and you'd get to do it again. So these systems being self-adapting was kind of a crucial aspect of the peer-to-peer. Okay? All right. Questions on the location piece? All right. So now, I told you this last time, but I'm going to repeat this. So OceanStore sort of use this notion of versioned objects, where every write gives you a new version, and each version's read-only. So basically, it can have a permanent name, and the permanent name ends up being the hash over the data. Okay, and thereby I could put a permanent version into the infrastructure, into the Dolar. I could copy it many times, and when I go to get that version, I put a query into the Dolar system with the hash, and it routes me to the data. So basically what you could see in this picture here is, for instance, this red thing could be the first version, and the purple one could be the second version of the data. And by routing to the hash over the red data, I'm getting the first version of the data. Okay? And I can get the first version no matter where I am, because versions don't change. They're read-only once they're copied. So that GUID is the same anywhere in the world. Okay? And so each version's read-only. It basically makes it easier to make sure we have copies, because we're not trying to copy something that's changing. We're copying a read-only thing. And thereby, you say, now wait a minute, but versions are changing. How do we know what the front version is? Well, the front version ended up being assigned mapping between the name, which we really go after, like Etsy password or something, and the latest version. And who does the signing? The responsible party does the signing. Okay, so it's up to that service provider to make sure we have a copy of or we have a pointer to the latest copy. Okay, and this was the common analogy where updates kind of go in and versions come out. All right.
Will it change something
yes.
at one end of the system?
Oops, sorry.
Will
Go ahead.
it take time to percolate to the other?
Well, that's a good question. So how long does it take for a change? Sorry, I totally lost my position here. One moment. Dun, 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 dun. I think I'm right. Close to here. Yes. Say again. So if I write something at one part of the system, how long does it take to propagate?
Yeah, you get like temporal inconsistency.
Yeah.
You look something up and get one answer, and you look it up and get a different answer, and then come back together and you disagree.
So notice the temporal inconsistencies you worry about is if I manage to get a previously signed version, which we call a heartbeat, I might think that a previous version was the latest version. When I go to look for the data, I'm actually using a read-only hash. So if the two of us look for the same version, we're never going to get inconsistent results. It's inconsistency about what the actual head of the comet is. Okay? And the way to look at that is that there is somebody, which is our service provider, who's responsible to make sure we can get the latest heartbeat, which is the signature, if we ask. So if you really care about the absolute most recent copy, you have to actually ask your service provider. And that sort of gets closer to a centralized server view of things, but the only thing you're getting there is the signed certificate. If, on the other hand, you don't care for the absolute latest version, but you can allow a little bit of outdated versions, then you can ask for local copies, and you'll know that it's valid because you have a signature, and it could be within some slop of the most recent version. So it's a question of sort of how close you want to get to the center of your service provider in order to get the most recent version. So there's always this trade-off between the how accurate your view of the latest copy is and the performance. And not every time do you need to have the absolute latest copy. Now, what I will say here is, now you might ask this question, what happens if multiple people write at the same time and they don't have the most recent view? There's two things we could do. One, we could make them all serialized by talking to the center, in which case it's slower. Or we could let them go ahead and make their changes. And if there's a conflict, we have to do what's called conflict resolution. So for instance, take the calendar. I put something on, I put something at 2 o'clock. They put something at 3 o'clock. The fact that I wrote those two things independently are still mergeable later because they don't conflict. So in many cases, conflict resolution is easy. And it's only those cases where it's not so easy that things get interesting. And so we actually provided an API that lets you trade off conflict resolution, which is the potential of failing because somebody has conflicted with you, versus time to go all the way to the center and grab a lock on the center server. Okay, and it's really the role of the responsible party that sort of handled conflict resolution when we cared. Okay, that's a complex topic where I don't need to go too much more in, but I think it gives you the flavor. So I kind of said there was two types of data in the OceanStore. One was what we called floating replicas, which you've already seen. Those are the copies of the data that are ready to go. Okay. The other thing, though, was how did we get our 1,000-year time frame? This was OceanStore's stable store, which is we take the data, we encoded it in what's called an erasure code or a Reed-Solomon code originally, although we're doing better than Reed-Solomon afterwards. And the idea is you encode data in n fragments, any m of which are sufficient to reconstruct. So I would say that Reed-Solomon codes are like the mathematical equivalent of a hologram. It's literally you put out n fragments, and as long as you get m of them back, you can still reconstruct. And it's any m of them. Okay? And so, for instance, for a storage overhead of 4, we might have a situation where we put n little chunks out, or 64 chunks out there. As long as 16 of them get recovered, you get all your data. And that turns out to have a storage overhead of only 4, and you get extreme durability there. Okay, because the question is, what's the probability that there are not 16 out of 64 servers still up? And so you can imagine that that's a pretty high, or a pretty low probability event that you lose it. Okay. And most of the data is archival because, remember, we're storing old versions of things in OceanStore. So most of the data is in the archival form. So I showed you this path. So suppose here are our floating replicas. Suppose I actually want to make a change to my data. What I would do is I'd push a change to a set of servers on my responsible party that are going to execute a Byzantine protocol, make my updates, sign them, and send them back out. And so now what's being stored here is the most latest version as well as a previous version. Okay, and by using the Byzantine agreement algorithm, there's somebody, our responsible party has a way of guaranteeing that they check the access control and that I'm really allowed to write, even if a few of the servers in that Byzantine group are compromised. And so we use Byzantine agreement as a way of guaranteeing the signatures. Okay? Questions? And so there's here's some pieces. Let's see. We also were automatically able to build a tree for this distribution. I won't go into this detail, but automatically built it based on queries so that we always had copies close by to people who are using them, and we had a way to push updates out. So the caching was self-constructed trees, which was kind of nice. So this is like a content distribution network, which I'm sure you've heard of. OK. And then finally, this is an example of the same update I showed you earlier, but here it's sending the fragments out. So with every update, you send out fragments. And they were the ones that were the sort of archival store. So instead of tape, we actually pushed out into fragments. OK. I think that's mostly what I'm going to say, except that I wanted to show you this notion here, which is kind of fun. So for the same storage overhead, so the fraction of blocks lost per year basically says that I have the data out being stored in OceanStore, and every, let's say, 6 months, I gather the data, and I make sure that I have the right number of copies out. So if I had 4 copies originally, every 6 months I look, and if I only have 3 copies, I make another copy. Okay, that would be one possibility. And what this fraction of blocks lost per year says that if I do this repair every, say, 6 months or 12 months or 18 months, what fraction of the blocks do I lose? And what you see up here, very close to the top, is a replication factor of 4 copies. And notice how it very quickly converges to the point that I've lost almost everything if I wait for 6 months to repair. Whereas if I use an erasure code, which is 64 fragments, any 16 of which are sufficient to reconstruct, and I repair every 6 months, you can see here that the fraction of blocks lost per year is down here in the 10 to the minus 35 or 38 or something, okay, which is an extremely small fraction. So just by encoding things in erasure codes, and think of this as a RAID on steroids, that you can do much better. OK, questions? All right, let's take a brief break, come back, and then I want to talk about operating systems again. All right. So let's talk about many-core operating systems. So if you remember at the very beginning of the term, I kind of gave you this picture, which was the 80-core multi-core chip from Intel back in February 2007. And the, that didn't transfer too well, but sorry about that. The Intel single-chip computer here, which is more recent. And the question was kind of, how do you program something like this? And maybe you use 2 CPUs for video and audio, 1 for word processing, 1 for the browser, and 76 for virus checking or something. And we sort of argued that perhaps that was a bad use of processors. So if we got parallelism coming into play here, and the question is sort of what can we do with it? Well, let's back up a moment and sort of say what might we actually want for services in our modern applications, and sort of what system support do we need? And should we just take parallel Linux or Windows 7 and be done with it? Or do we want to do something new? And if you look at these operating systems, there's a lot of functionality that was originally developed for uniprocessors, and they've been trying to port it to multiprocessors, but there's a lot of sort of leftover code. And I never told you guys this. I forgot to mention it but in class, but a few weeks ago, or maybe a month ago, we had a meeting with Microsoft, and it turned out that their virtual memory manager, which is the thing that does paging, is 300,000 lines of code. Okay, so you can imagine how likely is it for those 300,000 lines of code to be correct? Yes?
Is it in C?
Yeah, it's written in C. So clearly the new kind of parallel, so basically there's a lot of functionality in existing OSs, and maybe we want to start over again. Clearly new applications that are going to run on multi-core have explicitly parallel components in them. How do I know that? Well, Intel is banking on you being able to use a 64-core processor in the future on your desktop. Okay, so that means you better be using parallelism in some way, or that's a waste. Okay, and unfortunately, a lot of the parallelism that are in desktop applications is kind of hard to find. Okay, because it's different from sort of embarrassing parallel applications. And so we want to make sure that whatever we provide for support in the operating system, it doesn't destroy the parallelism that we worked so hard to get. Okay, and obviously new systems need to interact well with the cloud, whatever the definition of the cloud might be. And so that means that potentially we need to fit with extensive remote services very well, deal with security vulnerabilities well, and so on. There's going to be real-time components because everything we're doing today has some video associated with it. There's new sort of tracking your movement kind of things that are happening. I don't know if you guys have seen the new, the new Xbox Connect that came out. So that's based on some research, Project Natal at Microsoft, which is all about sort of tracking where your body is and then reflecting on it. All of these kind of things are going to be there, and you're going to want to use them well, and they all require some real-time support. And to get good real-time support, we want to make sure, once again, not to be interfering with the real-time support, which possibly leads us to wanting to start from scratch on our OS as well. And then, of course, there's responsiveness requirements. Okay, nobody likes listening to music and pulling a window forward and getting a glitch in your music, right, or your video glitches or whatever. A lot of us are used to that. It's like, it's part of the process, but there's no reason for it. Okay, and so maybe we want to make sure that we are more careful about what resources we use. So basically, if we have a lot of cores, maybe we start from scratch, and maybe we can do a better job at getting some of these. And actually, in Parlab OS, we have what I call the Rapids goals, which are, one, responsiveness is at the top. So we meet all of our real-time guarantees. We give you a good user experience, the illusion of very fast I/O, even though maybe you're talking to the cloud, like we were talking about with OceanStore. Real-time apps just work. Agility, which means that as you're changing from environment to environment and the network comes and goes, it just works. Okay, it shouldn't be the case that your system, because you went from 4G to 3G or to wireless, suddenly it breaks and you got to start it over again. Okay. Power efficiency. Okay, one of the most important things that everybody worries about today is energy, and it ought to be that whatever system we have, it ought to be able to measure the power and use it well. Persistence. Okay, this is one thing that I like to worry about, which is it ought to be the case that data is always in cyberspace somewhere, and so you never lose data. It should never be the case that walking across the street with your laptop, having your laptop run over, should never lose data for you. Okay, now you may be squashed and not really care much, but hopefully your data will survive. Okay, and then obviously security and correctness is important. Okay, so unlike traditional goals, which we talked a lot about this term, which are let's get the high throughput, let's use our CPUs as 100%. You know, all of those traditional goals, we're kind of going for these different, more user-centric goals. And so I like to think of this as taking yet another step. Remember at the beginning with the history lecture, where we're kind of starting with big rooms and you know everybody's in service of the mainframe down to more and more user-centric. Okay, and this is the ultimate user-centric kind of viewpoint. So what's wrong with current operating systems? Well, they often don't really let you express the things that the applications need, like I need a minimal frame rate to do well on this video, or I need a minimal amount of memory bandwidth, or I need some minimal quality of service. Okay, oftentimes there are no interfaces with the operating system for this. Okay, they often don't give you guarantees. Okay, they don't give you good performance isolation. That's that glitch problem I mentioned, where you're listening to audio and you do something else and suddenly the audio glitches because it didn't have enough resources. Okay? They often don't give you full custom scheduling. Now, why does that matter? Well, if you remember, you did a couple of different schedulers this term, right? There was priority scheduling, there's lottery scheduling. We talked about a bunch of other ones. What's the perfect scheduler for all applications? Okay, there isn't one. Okay, and so what's the approach of Linux and Windows and all that? They've tried to put, their schedulers are really complicated and they're trying to do, they're hacky, right? If this, do this, otherwise do this, if this, you know, there's a bunch of heuristics to try to schedule the resources well. Okay, and that's just, you know, that's just never going to work for all applications. What you'd really like is you'd like the scheduling to be 100% based on what the application needs, not here's this big monolithic thing I put together that hopefully does well for most of my apps. Okay? And of course, we all know they often don't give you sufficient security or correctness. Okay. So, because we've got many core, one, we've got we got many more processors, which possibly can make the fact that we don't have these guarantees even worse. But it kind of gives us an opportunity to throw everything out and restart. Good example, if you have enough processors, maybe it no longer makes sense, under all circumstances, to use interrupts to interrupt a processor. Maybe it's better to have a processor that spins with some really low power mode waiting for an event to come in because you don't need that processor for anything else. Okay, now that requires a little tweaking and thought. Now I'm not saying that's always a good idea, but it's the kind of thing you can start to think about if you have a lot of processors. Or you can start saying, what if I dedicate a given processor 100% to this task? Now I know that that task will not be interfered with by anybody else. Right? So by dedicating resources, I can get better guarantees. Okay? And so that's why I would say that mini-core basically lets us reevaluate how we do resource control in operating systems. And that's kind of where tessellation came into play. Now, the first step to this is this notion of two-level scheduling, where rather than this monolithic scheduler that's in the middle of everything, we divide it into two pieces. So the first piece divides resources up and says, on a per-task basis, here's the resources you get. Okay? Now notice that resources in this instance mean here's the number of CPUs you get, here's the amount of memory bandwidth, here's the amount of I/O bandwidth, here's the, you know, you could come up with whatever resources you want. At one level, we hand those out, and then we make them stay that way long enough that the second level is a application-specific scheduler gets to use the resources any way they want. So rather than having this big scheduler switching between threads on completely unrelated processes, what we do instead is we hand out resources to each of the processes, and then they get to use them any way they want so that you get maximum behavior. Okay? Questions? Yes?
Those resources, they don't actually go into user space. They stay in the kernel, but they're just associated with
Well, so the question might be, what does it mean to go into user space? So in fact, when I hand resources, the thing that's running in user space gets to use them any way it wants. So the scheduler in this case is actually running in user space.
Doesn't that mean you could potentially change what resources you have?
No. So the handing out of resources is the thing that's done in kernel space and is unchangeable, whereas the using of resources is done at user space. Question, yes?
So this is kind of built on the principle that application developers know the best way to use resources to get their tasks done. So you should let them decide.
So good question. So the question is this built on the notion that application writers know the best way to use resources and therefore you should let them figure it out? So yes and no. On the one hand, application writers, and by them I'm also including the library writers and so on underneath, do have a better sense of how things are used. Okay? But in many cases, it's not so much about knowing exactly how to use things, but knowing that what I've got right now isn't going to change or go away for some period of time, and so I can build predictive models of how things are, and I can figure out what I need. Okay? If you really say that the application writer, every application writer has to write a scheduler, well, you guys wrote schedulers this term, and imagine how many applications would get written if everyone had to write a new scheduler, right? Instead, the viewpoint here is going to be more that you're likely to link as a library one of n schedulers based on what you think is the right thing to do, and furthermore, that these schedulers are going to be doing sort of predictive models of what your performance is to figure out how many resources you really need. Okay. So, any other questions? So here's a base. Yeah, go ahead. Sorry.
So how would you go about like figuring out how much resources you need, like based on like different CPUs, actually more like CPU time?
So I'll get to this in just a second, how you figure out what you need. But basically, one of the big things we're getting with two-level scheduling is we're getting what I'll call performance isolation, which is that if I can give resources to an entity, and those resources are guaranteed not to go away for some sufficiently long period of time, then I can run that entity and see how it's behaving. And I can see, well, I don't have enough of something or I have too much of something. And then I can adjust. The alternative is sort of multiplexing all these resources continuously. Then it doesn't give me the ability to measure anything, and then I can never figure out what I really need because there's too much interference. So the two-level scheduling is as much about performance isolation, allowing me to build models of how I'm going, how things are working, as it is about explicitly using my resources in whatever way I want. Okay? So one of the big ideas here is spatial partitioning. And so here's a chip with 64 processors. And so the idea is a spatial partition is a group of processors with a hardware boundary of some sort. And so here we show the idea here that we've got kind of a partition with 16, another with 16, here's one with 4, here's one with 8, and so on. And these boundaries can actually represent hardware asserted boundaries where the data that happens to be within a partition is protected from another partition, even though these things are all running at user level. Maybe the memory bandwidth within this partition is guaranteed even if somebody else tries to use too much memory bandwidth and so on. So these are potentially actual guaranteed boundaries, depending on what kind of hardware support you've got. And they can also represent security and performance boundaries. I guess I said that already. So each partition potentially receives a vector of resources, so some number of dedicated processors, some set of dedicated resources, some guaranteed fraction of resources. So this partition here might get a guaranteed 20% of the file service, or something like that is another guarantee that you could imagine here. Okay? Now, so we've actually done a bunch of experiments, and and I'm not going to go into this in great detail, but I do want to point this out, that if you have two applications running on a 64 processor machine, one option would be to let the two applications each have 64 processors and just have a scheduler that multiplexes between them. That would be kind of the view of what we've gotten up to this part in the term. The other would be to divide the processors up so that application A gets some amount and B gets some amount, and they don't intersect with each other. Okay, that would be hard partitioning. And what you see here is the red one is time multiplexing in the more traditional place, And the best spatial partitioning, this is time to completion, is actually better than half the cost if you sort of do that optimization experiment and find out I give this many processors to the first thing and this many to the second thing. It's actually better to hard partition in some cases from a performance standpoint. And notice that I wasn't even really talking about raw performance as the key driver here. I was talking about performance isolation as the key driver. But even this shows that performance can be enhanced by partitioning. Okay, so that's a little counterintuitive, maybe. Can anybody figure out why this might be this way? Why might it make more sense rather than giving multiplexed 64 processors at the same time to two things? We actually split them out so that process A gets 4 processors and B gets some number. Why would that make sense? Why might that be faster? Yes? What about context switch? So you save some context switching. There's actually a more predominant reason for this. So applications don't necessarily run well at 64 processors. They might run more efficiently at 8. And so it turns out that if you go from 8 to 16 to whatever, you're actually not getting a linear speed up. You're getting some tail off. And so it's more efficient from a total system standpoint to use less processors and run for longer than it is to try to use more processors. Okay, so there's actually, because of the way the speed ups aren't perfect, it turns out it's better to partition in some cases. Yes? Yeah, this is a pretty good machine emulator. So, because we don't have a 64 processor machine that has these properties to it to play with. So, so the thing is, of course, giving 4 processors for all time to some process clearly doesn't work. So we have this notion of space-time partitioning, which is basically this idea that, yeah, for any given slice in time, we might partition, this 16 processors into, 4 for this task, 8 for this, 2 for this, 2 for this. But then over time, things are going to vary. Okay, and so we actually have a series of time slices where we repartition at each time slice. Okay, and that's the space-time partitioning piece. And so here, for instance, we have a green app that's always running. Okay, and maybe this is something that has really extreme real-time guarantees that can never be disturbed, whereas we have something else that can get 50% of the processors and processor time, and that works fine. And the key thing here is, unlike regular scheduling, which we talked about all term, where the boundaries can change at any point, we put more of a coarse-grained scheduling here. So again, for performance predictability, we want the thing running here in this pink cell to actually have the processors for long enough to predict the performance well, rather than very fine-grained partitioning. Okay? And so I call this controlled multiplexing, not uncontrolled virtualization. Okay? And uncontrolled virtualization is closer to what people currently do with VMs. All right? Now, we actually had a new abstraction we put together called the cell, which is a user-level software component with guaranteed resources. So you can imagine here that the pink thing is actually a cell. And what does that cell have? That cell has 8 processors for 50% of the time. Does everybody see that? So that cell has a guaranteed throughput of 8 processors for 50% of the time. Okay, so that's our cell. I don't know, is it a process? Is it a virtual machine? Hard to say. But it's different from the typical virtual machine environment because you have guaranteed resources with very predictable performance. Properties of the cell. Well, once you give the resources to a cell, the cell can build a user-level scheduler and do anything it wants to the resources. Okay, during that time slice, there is absolutely nothing that other processes can do to screw you up. Okay, and it actually communicates with other cells via secure channels, which I'll show you in a second. And when mapped to the hardware, so those are those periods of time where it actually has the hardware, you have gang-scheduled hardware threads, which are called hearts in the parlance of the Parlab. Guaranteed fractions of resources, such as physical pages, cache partitions, memory bandwidth, guaranteed fractions of system resources. Okay. So here is, for instance, how you might imagine building an application in tessellation. So the core application is parallel with 16 processors, let's say. It would have a channel, secure channel to connect up with a parallel library, which might have 4 processors. And what do I mean by secure channel? Well, actually the setup of this communication channel goes through some authentication process to make sure that you're really allowed to talk to that library, and the library is really allowed to talk to the application. Okay, so this is kind of where we get our security model. And we're sort of basing the actual physical chunks of resources on the way the app was originally structured. So for instance, you could imagine here, let me see, I want to get this rest of this picture up. There we go. So for instance, a real application might have a parallel library piece it talks to, which talks to, say, the file service, which might talk to device drivers, which might talk to real-time cells. And so what we did is we divided, in this case, the application is divided into a set of cells, each of which has a different type of scheduling or security domain. So the real-time cells might have scheduling for real-time scheduling, okay? Which I guess I won't get to talk about because we're running out of time. But EDF, for instance, is an example of a type of real-time scheduling. This might have a schedule that's built, specifically a scheduler that's built for high performance. Okay? This parallel library might be separated out because it's tuned in a certain way, and if we allowed it to be merged in with the core app, then the tuning wouldn't necessarily work. So by giving it an isolated cell, we can tune that library to work really well with 4 processors. And then, of course, the device drivers are kind of a whole other security domain. So in principle, the device drivers are running in cells, each with their own guaranteed resources. Okay? Is everybody with me? So it's a slightly different model. And it's all about the communication. So for instance, imagine this. Here's the shared file service. I'll quit here in just a second. You've got applications A and B are both talking to the shared file service. And what do we know about that? Well, it's possible, if we don't do this well, that A could do a whole bunch of writes and thereby prevent B from getting file service access. Okay, a great example of this is, I don't know if you've ever tried running 2 apps, one of which is using so much memory it's swapping all the time, and the other which doesn't really need memory at all. How do they work? Right? Neither works well. Right? The one that's swapping all the time actually screws up the one that isn't swapping because it keeps swapping it out. All right? So you have a similar problem here, and since we're giving guaranteed fractions of the file service, what we need to do is make sure that the file service keeps track of how many requests per unit time it's getting from each of the apps, and it tracks that. And if A tries to ask for more than it's allowed, it actually gets slowed down. So it'll force A to slow down so that B gets guaranteed fraction of the file service. Okay, so this is a very different view of resources from the way a normal OS works. We actually have kind of service level agreements at all levels of the system. Okay. Now, so here is kind of a fun view of what tessellation might look like, right? So we might have a bunch of large compute-bound apps. We might have device drivers are part of the processors. We might have windowing parts. We might have network and virus checking, intrusion detection in parts of the system, and so on, file storage. Okay? Now, to close out, and here's maybe a big compute server where we have a bunch of chips, each of which has 64 processors. And so we get QoS guarantees on communication, maybe with the cloud, communication to the disk drives, and so on. So we're basically trying to do quality of service throughout the system. Questions? So just to close this notion out, so 2-level scheduling. The first level is about partitioning the resources globally amongst the cells. And that's where we essentially potentially run an adaptive algorithm that figures out, based on the way that the thing is performing, how many resources does it need. Okay? The second level is purely application specific. It's able to use the resources any way it wants once it's been given them. Okay? Everything runs at user level. It can switch any way it wants. It can have any type of scheduler. Okay? And it's tuned to the specific application. Okay. Now, I wanted to show you, so we basically build a resource graph, which I don't have time to talk to, but I wanted to show you this notion here that there are several layers of tessellation. There's a policy layer, which is handling out resources. And the way it's handling resources is by putting them into a resource graph. And the mapping layer then decides how this resource graph, where there are cells at every one of these parts, get mapped to the real hardware over time. Okay? And then this is the final sort of big snow job slide I'll show you. So here's our allocation architecture. This is going to answer the questions earlier of what sort of thing would we actually do to figure out resources. So at one level, we have the partitionable hardware resources. So this is hardware. The kernel for tessellation has a partition mechanism layer whose job it is